a 1D number k, okay, and we wrote this like 1 over factorial k product from 1 to k of d chi of 1 chi minus a chi minus a minus epsilon, okay, and then there is product of I less than j of chi ij squared, chi ij squared minus epsilon squared, and then chi ij minus epsilon 1 squared, chi ij minus epsilon 2 squared. Okay, so this was the partition function of n equal 2 from which to extract the prepotential, just taking the log of this object and multiplying by epsilon 1 and epsilon 2. And from this partition function, I want to show that you can extract the Seiberg-Witten curve. Okay, the idea, as I was trying to explain last time, is that this chi I can be, which are the eigenvalues of the determinant that we need in order to compute the localization formula, okay, can be thought as being arranged in a certain Young tableau, okay, and each one of these eigenvalues are defined in one of these little box over here, and in the limit in which you take the winding number k, which is this object here, very large, and so the epsilon 1 and epsilon 2 are the dimension of these boxes, okay, as can be seen from the explicit solution. This line over here, okay, just becomes a smooth curve, okay. This is a procedure which has been around for some years, okay, also in matrix models, okay. So how to proceed? Okay, the first point is to take the sum over all the winding number. So we just write a kind of parameter which distinguishes the different winding numbers, and we rewrite this integral, okay. So instead of rewriting the integral, let me just take a sum over k and put a qk here, okay. And then what we do, we just exponentiate. We call this object, let me call it pi of chi of I, just for reason of simplicity, okay, and this like this, okay, or maybe chi minus epsilon, which is simpler, okay, just to make things simpler, okay. And then what you do, you just exponentiate this object. So this I can write like sum over k qk of product of d chi I, okay, and then 1 over k factorial if you want, but now it's not so crucial. And then we write exponent, okay, of sum over I. We distinguish these two parts. I mean, this part in which there is just a product over one index, and this part in which there is a product with two indices. So this becomes minus log of p chi I, okay, minus log of p chi I minus epsilon, okay, and then plus I have here a sum I less than j, which is this product over here, okay, and then we make an expansion of the logs. We exponentiate and we expand these logs. So what we get something like log of chi I minus chi j, okay, and this is this term, with all the tools, I mean, plus log of, when it comes to these terms, I take chi ij out, so this will become log of chi I minus kj like this, and then plus log of 1 minus epsilon over chi I minus kj, for example. Okay, just taking out chi ij out of this log. Okay, and then we can do the same for this, so we get a log of chi ij minus log of 1 minus epsilon 1 squared over chi ij, and then another minus log of chi ij minus log of 1 minus epsilon 2 squared chi ij. Okay? And then probably I have to close here this, yes, and I have to close also these parentheses. Okay? So let me keep on in this computation, okay, which is the computation of this saddle point. Okay. First of all, I notice, okay, this chi ij is chi I minus ij, so there is a cancellation of these terms. Okay. And then what I can do, given that I will be finally interested to epsilon 1 and epsilon 2 small, because they are the size of these boxes, okay, I can expand these logs in powers, okay? So what comes out is just sum over qk, okay? This is sum over q, and then just product over I, okay? And then here we have now the exponent. I just rewrite these two terms, okay? So this will be sum over I log of p chi I and plus log of p chi I minus epsilon, okay? Square parentheses, okay? So I just take these two terms. And now I expand those terms over there to second order. So first of all, I go from I less than j to I different from j, okay? And then I write for these terms, there is the linear term, which is just this one, okay? Then there is the square term, which is just chi I minus kj, okay? Squared, okay? Then epsilon 1 over, okay, I don't see from there, epsilon 1 over chi I minus kj, okay? Plus 1/2 epsilon 1 squared chi I minus kj squared, and then the same for epsilon 2. Okay, then I have to write like this and like this. Okay, so this is just the expansion of this log, and this log in powers. Okay, now this epsilon here is just epsilon 1 plus epsilon 2. Okay, So what I can do is I can just square this object, and what happens is that there is a cancellation with this term and this term, okay? So the final result of this computation is just sum over k of qk, okay? Then product over d chi I, which goes from 1 to k, and then you have exponential, okay, of sum over I. There is a 2 here, because I've changed the sum. Okay, because what I can do now is to expand also this one in series, so I can put a 2, because it goes with the term here, then there is an epsilon p prime chi I over p chi I, okay? So I treat also the term. And then what is left of this cancellation, so this is I different from j, what is left of this cancellation is just the term which I'm writing here, okay? So it will be epsilon 1, epsilon 2 over chi I minus chi j squared. Okay, very good. So this is the final result of this computation. Now what we do, we go from discrete values of the eigenvalues, okay, to the continuum. So let's introduce a distribution of these eigenvalues, okay? And this means that I write an eigenvalue density of this form, okay, which is such that dx rho of x is equal to k epsilon 1 epsilon 2, okay? So you see that in the case in which k, which is the winding number, becomes very large, this epsilon 1 and epsilon 2 are going to 0, okay? And then what we have to do is we rewrite this object here, okay, in terms of this rho, which is this density, okay? This is simple, and the result is this. This becomes an integral over this d rho of x, and then e to the minus twice epsilon 1 epsilon 2, then dx log of p of x over q times rho of x plus 1 over epsilon 1 epsilon 2, and this becomes dx dy rho of x rho of y x minus y squared, okay? So this is just the continuum, the form of these objects here, okay, in which we have introduced a density of eigenvalues. So now we have to solve this problem. We have to do the saddle point of an integral which looks like this. Okay. The first thing we do is to change this distribution and to go from this rho of x to another distribution, which is f of x plus 1 over 2 sum L goes from 1 to n, okay, and then x minus AL, okay? Now, the reason why we do this is because I don't have time, I mean, to show it, but if you take, I mean, such a Young tableau, okay, then this line here can just be written like this, okay, in terms of this object. So it makes sense, I mean, to go back, I mean, to this distribution. I haven't changed much because after a while, what you can see is that the second derivative of rho is equal to the second derivative of x plus sum over delta x minus al, L from 1 to n, okay? This is just a property of the modulus, so it is simple. And what you can see is that if you have a line and you have a cut, like here, in which there are the eigenvalues, your eigenvalues are here. And if you do an integral, okay, of this distribution, something like rho of b minus rho prime of a, you just integrate once this formula here, what you get is that this is 0, okay, minus integral for a between a and b of f second x plus n. Okay, so this is just a normalization. Okay, this is just telling you that the total eigenvalue number of eigenvalues which are in this cut are n. This is a boundary condition that you have to add to your problem. Okay? Now, okay, we have to massage a little bit this this integral. Okay? And let me show you how to do it. What I want to do is to get to a formula in which instead of this rho of x, I use this f of x here. So the first step would be to just substitute instead of rho of x, this f of x. Okay, and I want to get to a formula of a certain object, okay, like this one, for example, make the variation of an object like this. Okay, so I want to come to a formula like this, dx dy, okay, f second of y, and then x minus y log of x minus y minus 1, okay, delta of f prime x is equal to 0, okay, because I have to do the saddle point. So doing the saddle point means just taking the variation of this object, okay? If you call this a kind of Hamiltonian, what you want is you want to take the variation of this Hamiltonian, okay, and the final result will be this. Okay? If you manage to do this, then it is clear that the solution to your problem would be, given that this is an arbitrary variation of f prime, you have to set to 0 this part here in order to satisfy the condition of minimum. Okay? So the final result will be, now I'll show you how to get to this point, will be something like dy f second y log of x minus y equal to 0. Okay? That is, once I take the variation, okay, this object I can put back, I mean, into this form. Okay? And this is what I show you now. From here, what I can do, I mean, this is a function of x, is take a derivative with respect to x of this quantity, okay, and then what you get is just write this result. So let me show you how to deal with this part here and put it back in terms of f. This computation is just algebra. It's not very complicated, okay? So what you do is this. Let's introduce a function gamma x minus y, which is equal to x minus 1 y squared over 2, 3 over 2 minus log of x minus y. Okay? Let me introduce this function in such a way that double derivative of gamma of x minus y equal to double derivative of gamma of x minus y is equal to minus log of x minus y. And if you take double derivative with respect to x minus y, this is equal to 1 x minus y squared. Okay? So these are just simple derivatives. Okay? And I define a function which will be useful for what comes later. Okay? Now, let me see how I can get organized. Okay. So let me start from here. Okay. Sorry? 8 minutes. 8 minutes, I can do it. Okay, so you have h equal minus 2 integral of the x rho of x log of p of x plus the x dy rho of x rho of y x minus y squared. Okay, now we substitute. It becomes minus 2, and then dx rho of x, and this becomes just log of x minus ai, which is its definition for p, and then this becomes the x dy rho of x rho of y x minus y squared minus 2 sum over I. Then we can write this like rho second of x gamma of x minus ai plus the x dy rho second of x rho second of y, okay, gamma x minus y. So what we do is just we do a partial integration, okay, and we rewrite this formula in this way, okay? And then you come to writing in terms of this f of x. And this is what it comes out. Okay, plus dx dy f second of x f second of y minus twice f second of x, and this becomes sum over delta y minus ai and plus sum over ij delta x minus ai delta x minus aj, and this multiplies gamma of ai minus aj x minus y in this point. Okay. So what I've done is nothing that doing this transformation. Okay? And the final result for this computation, okay, is just this. That you can write this like sum over ij gamma ai minus aj plus dx dy f second of x, f second of y, gamma of x minus y. Okay? Which in turn, doing another integration by part becomes just this quantity that I'm doing. F prime y gamma prime x minus y. Okay? Now, this formula here is exactly of this form. Okay? This is exactly the form which I was looking for. Okay? It is interesting, but now I don't have time, to stress it further, okay, that there is this term, which is a term which is a perturbative term. So the funny thing is that you are doing something which is completely non-perturbative, okay, but then in the moment in which you do this transformation of going from rho to f, what happens is that there is a perturbative term that comes out. And this perturbative term is one of the reasons why now from AGT on, when we compute the partition function is always written as a combination of a part which is non-perturbative, contribution of instanton, a part which is perturbative, okay, which takes care of this, okay, and a part which is classical, okay? But this now is not important. Okay, the point now is quite simple. Okay, I have to solve this problem. Okay, this problem is an electrostatic problem. It's the problem of having, in 2 dimensions, okay, a certain electric field. You have certain conductors. Okay, you have the charge on the conductors. Okay, and you want to know what is the field, okay, that you are generating, okay? And usually the way in which this is done is you have to introduce an holomorphic function h of z, okay, which is just xy plus I v of xy. This is standard electrostatics, okay? And u and v are just the equipotential lines and the force lines, okay? And since this function is holomorphic, you have clearly these relations, okay, between imaginary part and real part, okay? And what you can do is clearly you can interpret the electric field like delta V over delta X and minus delta V over delta Y, okay? And finally, the total field EX plus EY is just equal to minus dV over dx minus I du over dx, which becomes minus I d over dx, and then u minus IV, and this becomes just minus a h prime of z, like this. Okay? Now this is an old problem, okay, which then ends with the Gauss law, because the Gauss law, which is 4 pi rho, is equal to this h prime of z, okay, which is nothing else than the modulus squared of the electric field, okay? And if you take, by any chance, the book by Berkeley on classical electrostatic, which is very elementary, okay, what we are doing here is that we have a field, an electric field which goes like this, is E plus, an electric field which goes here like E minus, and there is a certain thickness of this area, okay, these clearly are the same, but with opposite directions, and when you send, this thickness to 0, what you get is exactly this result, okay? How do you solve such a problem? Such a problem is solved, I need another 5 minutes, okay? Such a problem is solved with conformal transformations, okay? So let me show you how you solve this with conformal transformations. What you have to do is, if you have, for example, a charge, okay? There is a segment of charges, okay? If you have to draw what are the equipotential lines of this thing, okay? They go like this, okay? Now what you do this conformal transformation, which is omega cosh minus 1 of z, okay? And you go from the z plane, okay, to the w plane. The w plane, I mean, now the equipotential lines, they look like this, okay? And this means that here you know how to solve your problem, and what you can further do, okay, we'll do it later, you do another transformation in which you write these lines like this. It's even simpler, okay? Now, our problem is that this electrostatic problem is just telling us that you have many segments on which you have your eigenvalues. The charges just live in these pieces over here, okay? Now, what you can do, how you find, the conformal map. The conformal map, you have to use a formula which is called a Schwarz-Christoffel formula, which goes like this, okay? The form of the conformal map is the integral over z of pi over I, a certain bi minus z to these angles over pi minus 1. That is, I'm mapping this segment into a polygon like this, okay? At infinity, this is closed like this. And if, for example, let's take alpha 1 minus alpha 1 plus alpha 2 minus alpha 2 plus, okay, let me just take 2 for the sake of simplicity, okay? This is alpha 1 minus, this is alpha 1 plus, and this is alpha 2 minus, this is alpha 2 plus, okay? And then these are the angles. This is something like beta 5, which is equal to 2 pi, okay? Beta 1 here is pi over 2, okay? Beta 4 here is pi over 2. These angles here, okay, then clearly you have also here, which is beta 3 and beta 2, which are both equal to pi over 2. Then what you do, you take, these values of these angles. This is a map which sends, the line with these cuts into a polygon, okay? And you apply here, okay, with where the beta i's are just these eigenvalues, okay? Very good. If you do this, okay, what you find is that this object becomes product of x minus alpha I minus x minus alpha I plus I goes from 1 to 2, okay? This is what I want to go to this curve, which looks something like this, squared minus lambda to the 4th. This is where I want to come, okay? Now, for this polygon, okay, now, if we write the map, this is z, dz, and then we have zeta minus a certain constant, which is not important. I will set to 0 then, and then here I will have alpha 1 minus z to the 1/2, then alpha 1 plus minus z to the 1/2, alpha 2 minus z to the 1/2, alpha 2 plus minus z to the 1/2. What I'm doing is just writing this object with these angles, okay? Now, this can be written like this. If you define a P of z, okay, which is just z minus a, this becomes dz P prime of z over P squared minus lambda to the 4th, okay? In the moment in which I have this product and I write this product like this, okay, I can rewrite this integral like this. This one becomes 1 over 2i minus cosh minus 1 of pz of lambda squared, okay? And this is almost the end of the computation. If you perform now another conformal transformation, which is this conformal transformation is given by, this is w, say z prime, so the conformal transformation which is given by z prime equal to e to the minus 2i omega, okay? If you perform this transformation, this becomes simply minus I over 2 log of z prime equal to minus 1 over 2i cosh minus 1 p of z over lambda squared, okay? Now I can invert this stuff. I can multiply by cosh on this side, so this just becomes cosh of, I forget about now 1 over 2, which is not so important, log of z equal pz over lambda squared, which, remembering the definition of cosh with the log, becomes just 1/2 z prime plus 1 over z prime, okay? This is already the Seiberg-Witten curve. If you want to put Seiberg-Witten curve in a more familiar form, you just write y plus p of z over lambda squared, and what you get is p squared minus lambda to the 4th, okay? And this is the end of it. So this is a Seiberg-Witten curve for SU2, because we have just taken 2 cuts. Okay, so this is just what I wanted to say, okay? Sorry to have taken a few minutes more than what was needed, okay? Questions?